Giri is the first ever fully probabilistic model to identify and estimate risks associated with major geological and climate-related hazards across critical infrastructure sectors in all countries and territories of the world.
Infrastructure is essential to the well-being and prosperity of our citizens. Resilient infrastructure is designed to withstand shocks and recover quickly from disasters. To build resilience, our leaders, financiers, and experts have to be able to make informed decisions. They need to understand the risk infrastructure faces and how these will change over time. This is challenging because there is a data and information gap, particularly in the public domain. To address this gap, CDRI has developed a tool called Giri. Giri uses a proven financial risk approach to create a probabilistic model of future scenarios without relying solely on historical data. The platform provides publicly available financial risk metrics for every country in the world for 6 natural hazards and 9 sectors that have been modeled into Giri. Through this, the need for stronger policies, strategies, plans, standards, and financial investments become much clearer.
Giri is based on probability theory, integrating uncertainty into calculations. It is stochastic, combining natural physics and the randomness of hazardous events. Thousands of hazard simulations provide a comprehensive set of possible infrastructure impacts. The model is non-stationary, reflecting different scenarios of climate change at a national level of resolution, tailored for disaster risk assessments in infrastructure sectors. Giri's purpose is to improve the understanding and make the global landscape of infrastructure risk and resilience visible. In doing so, Giri provides a globally comparable set of financial risk metrics, such as the average annual loss, AAL, and probable maximum loss, PML, for infrastructure assets.
So for Giri, it's very systematically collected data on all the assets in all the infrastructure sectors. So we've looked at telecommunications, power and energy, roads and railways, health, education, ports, airports, and the building stock in general. And we've looked at the risk to a range of different hazards. So we've looked at floods, tropical cyclones, storm surge, landslides, earthquakes, and tsunamis. And using all this information, we're able to actually calculate how much is likely to be lost in each sector, each infrastructure sector, in each country, in each year. So this is really vital information for governments to actually start. Unless you actually know how much you're losing, you don't know how much it's worth spending to actually make this infrastructure more resilient.
Average annual loss. Average annual loss, AAL, as the name suggests, is an annual average of all the financial losses that might happen in the future due to probable hazards. It means it takes into consideration the total financial value of losses by disasters which have not yet occurred. It is a financial metric which is expressed in US dollars. Probable maximum loss. This refers to a loss that occurs infrequently, typically over long return periods. While the probable maximum loss, PML, is represented as a curve analogous to the loss exceedance curve, LEC, it is conventionally simplified to a single value by selecting a specific return period. In the insurance sector, for instance, return periods utilized to define the PML commonly span from 200 to 2,500 years. Relative average annual loss. Relative AAL is the ratio of a sector's AAL to its total exposure value in US dollars, indicating the disaster damage burden on that sector. Loss exceedance curve. The loss exceedance curve, LEC, encapsulates all essential information for understanding the occurrence of losses. It offers a comprehensive quantification of risk in probabilistic terms. While exact predictions of future disasters are unattainable, with the LEC it is possible to know the probability of surpassing any given loss threshold within a defined time frame. Metrics like AAL and PML are derived from the LEC, providing a comprehensive view of potential future losses. This knowledge aids decision-making in risk mitigation strategies.
Giri risk model consists on combining properly three different components, that is the hazard, the exposure, and the vulnerability. In the Giri includes in the 7 different hazards, some of them climate-related, that are modified by climate change. Then the exposure includes building and infrastructure sectors, and the vulnerability was built through archetypes to represent in the best way how the different intensities of the hazard can affect that exposure. What we obtain is the loss exceedance curve. That is a curve that includes all the possible losses for different frequencies, and it is an exhaustive curve that includes the small losses with high frequency and bigger losses with lower frequency. Through this main metric, that is the leg, we can obtain other type of metrics that are very useful for decision making. That is the average annual loss, the probable maximum loss that can be used for different return periods, and that can help to build strategies in order to find different actions to mitigate risk and to prevent risk, and also to finance risk.
Step 1. Hazard input data was obtained by developing comprehensive simulations for all potential manifestations of hazards, including geographical distribution, intensity, and frequency. Step 2. The intensities and frequency of the hydrometeorological hazards were modified to account for climate change scenarios, SSPs or RCPs, reflecting a lower and upper bound. Step 3. The exposure database was assembled by geolocalizing exposed assets and networks in each sector from public data sources. Step 4. Economic values were assigned to exposed assets using a bottom-up procedure. Total value of the assets in each country was scaled to reflect the value of capital stock relative to others. Step 5. Vulnerability functions were developed for over 50 infrastructure archetypes, linking hazard intensities to expected losses. Step 6. The associated damage and loss for each asset was then calculated for each stochastic hazard event.
In the Giri project, we looked at 3 geophysical hazards, namely earthquakes, tsunamis, and landslides. For tsunamis and earthquakes, we decided to use the already existing data that were available since 2015. But for landslides, we had to develop a new model because of the way we were doing the quantitative risk assessment. So we worked almost exclusively on the landslide hazard in this project. Landslides are kind of a neglected geohazard. They're the most frequent geohazard. But since they're often triggered by an earthquake or extreme precipitation, in the disaster databases, you don't see landslides as being a major issue, because in these databases, the disaster is always classified by the triggering event. So if an earthquake triggers a lot of landslides that destroy a road or cause a lot of fatalities, is registered as an earthquake event in these databases. Now, for dealing with this landslide problem in Giri, we developed a model which looks into susceptibility of an area and the triggering mechanisms. And specifically, we looked at earthquakes and extreme precipitation as the 2 main triggering mechanisms for landslides. This is the first time that we have a global model that can be used for a scenario-based assessment of landslide risk. And there's, of course, when you're working on globally, you have to take a lot of shortcuts. So you cannot really zoom into details for every single building in the world. but we decided to focus on the transportation infrastructure, road networks and railways, which are long linear infrastructures that if the landslide affects any part of it, it would lose its functionality. And there's a lot of interest in this model, there's a lot of room for improvement, and we hope that in the future iterations of this Giri project we can improve on what we've built on so far.
Climate-related hazards that includes floods, droughts, cyclones, and landslides, triggered by rainfall. It's not easy to factor in climate change into a global model. It requires you to have some difficult choices and some hypotheses behind that. There is a wealth of climate information out there, several combination of SSPs, RCPs, and different models you could use. And we could not afford, to analyze them all. So we took the liberty of deciding how to go about it. And we decided to treat, the uncertainty, in the climate change component by having an analysis of the trends and selecting, the a lower bound and an upper bound in the climate, so that our risk computation will be included, actually bounded, by these two future scenarios. A lot of, the climate-related variables included in one derived by a global hydrologic model have been, shared among, the different hazards. So floods as well, droughts as well, as I was saying, all the rainfall characteristics, they are coming from the same modeling chain, so there is a consistency, among all models. The rest of the hazard, is pretty much, similar to what, the insurance, world uses a CAT modeling.
Giri offers a fresh approach to infrastructure risk modeling, though its accuracy will likely improve with further calibration. As climate models and hazard data advance, Giri's precision will increase. Vulnerability functions will also refine with use. While Giri enhances global infrastructure risk understanding, it doesn't yet measure the costs of service disruption or broader impacts on society. It is an advocacy tool for promoting risk-informed infrastructure planning and investments.
The platform is organized with three main sections. One stored all the geospatial, geographics, maps information and include mainly the hazard and the exposure models. The second section collects the risk metrics information under the form of dynamic dashboards. And the third section, it contains all the information layers. So we have three levels of information. The first one is the so-called general information, because include a glossary and all the papers, the background papers that will be used to build the different model. And of course, all the bibliographical references for people who want to go a little bit more far. The second level of information is by topics. For example, you can catch the information about the model of Giri with a short explanation, or for example, the information about the building exposure model, or for each of the different hazards. For example, here we have a flood example. Third level of information that is consists the metadata of each of the different data sets that are included in the platform, where metadata you can find all the basic information of the layer. And we have also the last layer of information that is the possibility to ask to CDRI Secretariat more supplementary information about a specific data set. So you can also use this possibility.
The Risk Metrics section offers interactive charts and maps on specific dashboards, showing performance curves, aggregated AAL, exposure by building and infrastructure, and key risk measures like AAL, PML, and LEC.
You can choose your topics, for example, cyclone or flood, and after this you have a data frame with the interactive dashboard where you can change the country or use other active possibility to filter your data.
After these, you can choose if you want to make a country-by-country analysis, the so-called country profile, or if you want to see a country comparisons. Let's consider a practical example. We start in a generic section and choose a country, in this case, Brazil, and we want to ask several questions. The first question is, what is the overall average annual loss for the country? You can find the answer in the different dashboards. Another question might be, what are the main hazards and how much impact do they have on the country? For Brazil, we observe that floods, earthquakes and landslides are the primary hazards. We can also examine how these hazards affect different types of infrastructure. Here we go in the section where we can take into account the different climate scenarios. So if we take the different climate scenarios and assess the lower and upper boundary figures, in the case of Brazil, you will see that the lower boundary is significant in changing the way of different infrastructure are affected for this country.
Basically, we have a data catalog where we have all the different data sets available and a data frame with the visualization and the analysis that we can be done. In concerning the selection on the layer, we have three different main sections. One includes a list of pre-selected data sets, the most important for your analysis. The second one is the full range of the data set. Now we have around 100 different hazard and exposure layer. And the third one is your special, your personal web space is a space where you can collect the layer from the other section, and you can make your specific analysis in this workspace.
We are now training people around the world to use Giri and are already working on Giri 2.0 by further developing the model to include more hazards and downscale it to provide subnational models. Our ambition is to build capacities in countries in the areas of infrastructure risk assessment and resilient infrastructure planning.